A, B, and C here in the Venn diagram. 10.1.1, it is given that the probability of at least one of the events is 0.893. If it's given, calculate the value of y, the probability that none of the events will occur. Okay. So first thing we look at is what is the probability of at least one? Probability of at least one is the probability of sort of this area of the Venn diagram. So we can, or at least one, we have this whole area here. That's our probability of at least one. Another way to look at that is probability of A or B or C. Probability of A or B or C. And this was given as 0.893. It's given in the question, 0.893. That's probability of at least one. Okay. What is the probability, question A, that none of the events will occur? Well, if at least one is 0.893, then the probability of none is going to be 1 minus at least one. 1 minus at least one is the probability of no events happening. This will be 1 minus 0.893 is 0.107. Well, this was A. Probability of none happening is 0.107. Calculate X, the probability that all three events will occur. Well, the probability of all three events occurring is the overlap of all three, which is this X area. So the dark green, which was supposed to be orange in the middle there, is the probability of all three events happening. This is our X. So we can take our probability of A or B or C, which was given as 0.893, and just minus all the other values that were given inside here. 0.05, another 0.05, another 0.15, a 0.2, a 0.1, and a 0.183. So that will give us the X in the middle. So 0.893 minus 0.2 minus 0.1 minus 0.15 minus 0.183. What have we left out? The two 0.05s. Oop. Okay. All of that in the calculator, and X is equal to 0.16. 10.1.2. Determine the probability of at least two of the events taking place. So at least two is the overlap of A and C, and the overlap A and C, and B and C, and A and B. So all of those added together, that's your at least two area. Probability that at least two events occur. So we have probability of at least two is going to be equal to 0.1 plus 0.16 plus 0.2 plus 0.15, 0.16. 10.1.3. Are events B and C independent? Justify your answer. So for independent events, we know that the probability of event A times the probability of event B must equal to the probability of A and B, or the overlap between the two, if they're independent from each other. So if A happening first, it doesn't matter if A happens first or if B happens first. Any of them can happen first. It's not a conditional probability. Okay, so we know this. So we can, let's first, which ones are they looking at? Looking at B and C. So we're looking at B and C. So let's rewrite that. We want that is the probability of B times the probability of C equal to the probability of B and C. Is it equal? Well, the probability of B, we can add up. So look at the probability of B, everything inside the green circle, and the probability, so it'll be 0.1 plus 0.183 plus 0.2 plus 0.16 is the probability of B. So the probability of B happening is 0.643. Probability of C happening is going to be everything inside this C circle. Everything. Oh, that was interesting color, but everything in the blue circle. Let's do this. There we go. So we have probability of C happening 0.05. Oh, 0.05 plus 0.2 plus 0.15 plus 0.16. Okay. The probability of C happening is 0.56. So those are our probabilities. Not enjoying this highlighter tool. Let's see if I can make it a bit better, bigger. A little bit better. Okay. So let's times those together so we know what P of B times P of C even is. So 0.643 times by 0.56. And this gets 0.36 is the probability of those two events happening times together. Now, what is the probability of B and C by inspection? Whoops. We can do this by inspection. Probability of B and C is the bit in the middle. Now I'm going to try and choose a color that changes the color. So here's B, here's C. Probability of B and C is the overlap between the two, the intersection between the two, which is 0.16 plus 0.2. 0.16 plus 0.2. Add those together on the calculator, and it does indeed equal to 0.36. Therefore, B, C, and B are proven to be independent events. Yes. Could add an extra thing at the end there because there's an upside down therefore is a because B and C is equal to B, probability of B times the probability of C. Okay. A 4-digit code is required to open a combination lock. The code must be even numbered and may not contain 0 or 1. And digits may not be repeated. So non-repeat situation. How many 4-digit combinations are there to open the lock? Now I'm going to straight away say that my answer does not match the mark scheme. The official mark scheme. Okay, so maybe somebody can put in the comments how the mark scheme got to their answer, but I'm going to do my usual method, sort of how I'm interpreting this question to see. So what I usually draw myself a box with, it's a 4-digit code. So the sample space has 4 options. And we're working with numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Now, my interpretation of this question is that your 0 and 1 are not allowed. So we don't have we're not allowed, it doesn't contain 0, 1. So those are already out of our sample. That leaves 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8 options. So currently we have 8 options for our sample space, and it's a non-repeat. So if there was no further information for non-repeat, you would just say 8 options is our first options times 7 times 6 times 5, and it would be finished. But of course, there's lots more information here, so we're not going to do that. Okay. So what further information did they give us? They said that digits may not be repeated. So, okay, that means once you've used a digit, you can't use it again. And it must be even numbered. So even numbered. Our even numbers, for me, if it's even numbered, in my interpretation, it must end on an even number. An even numbered code must end on an even number. So if you look at those blue highlights, those are all the even numbers that we have left to work with. There's 4 of them, 1, 2, 3, 4. So there's 4 options to end on. It has to end on an even number. Okay. Now, once you've used one of your codes here, so in this 4 option, you've used one of your numbers. So one even number will be used up there. So that means our first number, there were 8 options. So 1, 2, 3, 4, 5, 6, 7, 8. You've used one already over here. It's one even number, and that means we have 7 options left. One even number has been taken away. And this is times 6. It's a non-repeat. So the next one is 6. And then the next one is 5. And this is the counting principle. So we times them together. 7 times 6 times 5 times 4. I think actually I did end up getting the mark scheme amount. Let me just calculate that. 7 times 6 times 5 times 4. Fantastic. Well, actually, this was not in fact the case. So my answer does, in fact, in this case, match the official mark scheme. Wonderful. Okay, so 10.2.2. It's given that the code is greater than 5,000. So greater than 5,000 means that our code is greater than 5,000, means that it has to start on a 5, 6, 7, or 8. Again, this is my interpretation of this question. Might not exactly match the mark scheme. We're starting on a 5, 6, 7, or 8, but our final letter, number has to be even. And we've got a new condition that our third digit is 2. Our third digit is 2. That means there's always going to be only one option for our third digit. It has to be a 2. And it's also one of the even numbers. So just to bear that in mind, 2 is an even number. So if it has to end on an even number, there's only 3 even numbers left over that it can end on. So it has 3 even numbers to end on. And one of those even numbers is within the 5, 6, 7, 8, 9. So if we were to take out a 6, for example, then we have 5, 7, 8, and 9 left. Or if we were to take out an 8, we'd have 9, 7, 6, 5. So there's 4 options to start with. 4 options that are above 5 to make it bigger than 5,000. Okay. So now we've used up one here. We've used up another one here. These are both even. And this one is a 2 specifically. We've used up one here. And so now we want to ask, out of what is left over to put in the second block. So the way I see this is, well, 2 is gone. It can't be 0 or 1. So it can be, let's take a color. It can be a 3. Hasn't been used. 2, an even number has been used as a 2. 1 even number is used on the end. So this is an interesting case. So like, it could be a 4 if the 6 or the 8 was used. It could be a 5, 6, 7, 8, or 9. 5, 6, 7. How many places? The 2 is used. 1 even number is used. I think I count 1, 2, 3, 4, 5, 6. Intuition. Yeah. Let me check the mark scheme here for you. This is what I come up with. We had 8 options to start off with. 1 even option is used at the end. So there's only 6 left once you use 1 over here. But I feel like there's still more to this question. Options that the mark scheme has offered to look at. So they've taken it as 3 options. In an exam, though, just to finish this off, for your continued accuracy, and you can get method marks. So what I would do is just roll with it and say 4 times 6 times 1 times 3. Give my answer. 4 times 6, this, of course, just to be very clear, is wrong. 4 times 6 times 1 times 3 is 72. And it asked for the actual probability this time. So you want 72 out of 840 in its simplest form, which is 3 over 35. Okay. So this is what I would have got in this exam, not a completely accurate answer. Let's take a look at the offerings of this mark scheme. In fact, I think let me just fetch the 10.2.1. You can stare at as well. The mark scheme just starts with the odd numbers. So if it starts with an odd number, it's either a 5, a 7, or a 9. Or they have the option to start with one of the even numbers, and they've taken those probabilities separately and then added them together. So they're saying it's either it starts with an odd number, or it starts with either 6 or 8, and they've taken those as separate probabilities here, which is quite clever. So if it starts with an odd number, I see the second one was 5, so I counted this incorrectly. That must have been, there were 5 options left, not 6 options left. So if it starts with 5, 7, or 9, then there's 3 options to start. Then there were 5 left over once you take the 2 evens out. The 2 is always one possibility, and then there were 3 other even numbers left. So that's the first one. They started with an odd number, so there's still 3 even. Then we say, every time we say or, we plus, and is times, or is plus. Our next option they've taken, if it starts with a 6, there's, of course, it has to be 6. And this one has to be 2. There's 5 left here. And this time it's used in even numbers. So therefore, there's only 2 even numbers left over. And then there's another one of those. So if it starts with an 8, then there's 5 left over at the end. And it has to be a 2. And then there's 2 even numbers left over. So when you say in probability and, you times, and when you say or, you plus. So you can see they plus those together. So it would be 3 times 5 times 1 times 3 plus the next 1 times 5 times 1 times 2, and there's 2 of those. 1 times 5 times 1 times 2. There's 2 of those. Okay. Let's check if that should work out. And that would be our probability. This should equal to 65. And then we do the same method as I did in my incorrect option over here. We just take, because they asked for an actual probability, then we have 65 over the total from 10.2.1. The total number of ways the code could be was 840. And we want to fully simplify that and see it's better to give the answer as a decimal form. Okay. No, probability. Not my favorite, but fascinating how it works out. Right, that concludes the question 10, and I think it also concludes paper 1 from 2022, November, grade 12. If you like my videos, please like them and subscribe to my channel. Thanks so much for watching.